everyone, welcome to my video on how to find the area of any polygon easily. For starters, let me just kind of explain to you why this thing might even be necessary. So for example, in this screen you can see that I have given you the area for a few shapes. For example, the area of a triangle is 1/2 times the base times the height. The area of a trapezoid is the height of the trapezoid divided by 2 times the sum of the length of the two bases. Well, but if you look at the green one here, it's not so clear how you're going to find the area of that, right? I mean, sure, some people might say, oh, you could just break up the areas into smaller triangles like this, for example. But then that's kind of impractical because, well, first off, you need to know the area for every triangle, and two, that means you have a lot of dimensions to work with. And third of all, sometimes you might not even have enough dimensions to break up into triangles like that in the first place. And so therefore, I will show you a very simple method that allows you to find the area of any polygon easily. So first, let me quickly go through the derivation. But before I talk about the actual formula, I first need to quickly review Green's theorem, which is a theorem commonly taught in a multivariable calculus class. And we know that by Green's theorem, that suppose I had a simple closed curve C going counterclockwise. Then, if it's a simple closed curve, then you can see that there is a two-dimensional region D that is enclosed by it. Right? And what Green's theorem says is that if I have a 2D vector field F, where F has the scalar components F1 and F2, which are both a function of x and y, then Green's theorem says that the line integral over the closed curve C so it's equal to the double integral over this 2D region D of the partial derivative of the second component of f with respect to x minus the partial derivative of f1 with respect to y, dA. And we know that one application of the Green's theorem is area, because we know that the area of any two region D is equal to the double integral of 1 dA. And so if we want to figure out the area of any 2D region D, then all we need to do is just figure out f such that the thing I showed you above is equal to 1, right? Because once I say that this thing is equal to 1, then we know that this is the area of region D, which we can figure out just by figuring out this summat. All right, so that's cool. So we know exactly how to figure out the area of D. It's just that we need to figure out what F1 and F2 is such that this is true. And there's several examples that actually make this work. So for example, this works because the partial derivative of 2 with respect to x is 1, and the partial derivative of f2 with respect to y is 0, so 1 minus 0 is 1, so it actually works. And there's other examples too, but I'm just going to choose this one. And actually, the configuration of f actually doesn't matter as long as this condition is satisfied, so I'm just going to choose this, just for consistency's sake. Okay, all right, so now that's cool. So now we need to go back and figure out how can we apply this to the situation that we want? Well, for starters, a polygon which means that if I had a polygon something like this, for example, right, then you can see that this is a straight segment, this one is a straight segment, that one, and that one, and it comes back to itself. And since polygons never self-intersect, which guarantees that this is a simple closed curve, all we really need to do is just, well, figure out the value of f.dr over each curve, over each straight segment, and if we do the summation of all of them, then we can get back that thing that we wanted in the first place. Cool. And of course, we will use this f, like I said earlier. All right, so let's get started. So if we wanted to do, I'll just show you like just one of it. But basically what happens is that, say I wanted to go over C1. And let's suppose that C1 had a point P1 and P2. This thing, then we need to know f of r of t, where r, okay, all right, and then we also need to know what r prime of t is, and we need to know the time interval. And here's my assumption that I'm gonna make. To make things simple, let's just assume that it always takes 1 second to go from one point to the next. So we're gonna assume that our time interval is from 0 to 1. All right, cool. And once we have all of this, then we could just solve the integral, and then we're good to go. And it's just going to be the same for every single other curve. All right, so let's do this. So we know that we want to solve for r of t. But r of t is just a straight line. And we know that r of 0, so the vector at time 0 is just going to be p1. First figure out r of t. And r of t is just a line, so therefore it's just r of 0 plus t times r prime of t. And we know, and luckily r prime of t is very simple because it's just the change in r divided by the change in time, because the derivative is a constant since r is a straight line. And therefore we know that the change in r is r1 minus r0, so that's just x2 minus x1, and then y2 minus y1. Right, and then we know that the change in time is 1, so therefore r prime of t is x2 minus x1, y2 minus y1. And then we go back here, and therefore we obtain that r of t nice. And now we already know what r prime of t is. We know r of t, and now what we need to do is figure out f of r of t. That's the last thing, or at least the last setup before we start solving it for the integral. And so f of r of t will just be minus 0.5 times y, where y represents the y of r of t and x simultaneously. So then we just put, so then we know that y is the y from here, which is just y1 All right, nice. And then all that's left is that we take the dot product of f of r of t, dot product of r prime of t, right? And then once we figure out that value, which will be a scalar, we do the integral from 0 to 1. And this is going to involve a lot of, distribution, cancellation of terms, and etc. So just to get to the long story short, it ends up being 1/2 of y2 x1 minus x2 y1. A very easy way to remember this is that you just imagine like you had a small coordinates table like this, and you just put them in order, and it's just this way and that way, right? And then the one that goes this way is associated with a plus, and then the one that goes this way is associated with a minus. So therefore, y2 times x1 minus x2 times y1, and then you multiply all that by 1/2. And so therefore, because this represents one piece of curve, and we want to do it over several curves like this, so 1, 2, 3, 4, or the number of segments that we want, or the number of sides of a polygon. And so once we get that, then all that really just remains left is that the summation of all of this yields the answer that we wanted in the first place, where of course f satisfies the condition that the curl, or the simplified curl yields 1. Right, and so we're actually done because we already know what one of the answers look like. Then that implies that the area of D is basically this value, but summed at between every different point. And so hence we end up getting 1/2 times the summation from I equals 1 to n of yi plus 1 times xi minus xi plus 1 times yi. Nice. And this, my friend, is the formula. And now here are a few points that I want to make. First off, if you reach the last point, in, you might be wondering what would I do with I plus 1, which is n plus 1. But there's no such thing as like n plus 1 as a point because, well, you only have n segments. And so therefore what happens is that you go back to the first point when this happens. So as an example, say I had 5 sides, right? And I wanted to go between the 5th point and the so-called 6th point as a quote. What this means is that you're really going back to the first point. So the first point that you used in the summation, right? And second of all, I and I plus 1 have to be connected. What this means is that essentially you go like this. And what this means is that if you're going from here to here, you got to make sure that 1 is consecutive to 2 and 2 is consecutive to 3. And I think this formula is really cool, is because you don't even need to know exactly the shape, or you don't even need to know a lot about the polygon. All you need to know is just the number of segments n and all of the coordinates of each one. And once you know that, you could just essentially just find the area of any polygon. And that's the cool part. All right, now let me show you a quick example. And so here's my example for today. Let's say that I wanted to figure out the area of this thing. But let's say that you didn't know the area of the trapezoid, but you somehow knew that the area was this. So in order to make this work, here's my best suggestion, is that you create a table. And you pick a point that you like to start. It could be any point, but you have to go in counterclockwise consecutive order. So we start with 0, 0. Then the next point in that order is 6, 0. Then 4, 2. And then 1, 2. But to account for that part where you could have an n plus 1, we need to go back to our original point. So we go like here, and then back here. So then we write our first point again. All right, and then here's the method. And that is, what you basically do is like you go through this diagonal and you go, okay, 0 times 0 minus 6 times 0, which is 0. All right, and you just do it again. And
6 times 2 minus 4 times 0 is 12. And then you keep going, and then you go this like this. So then 4 times 2 minus 1 times 2 is 6. And then you repeat one last time.
And then you just add all of them up because you have to use a summation, and then you just multiply by 1/2. So hence we get nice. The final answer exactly matches with what we anticipated in the beginning. Yeah, so it's kind of nice that we see that there's a confirmation of all this. But you may think, well, why do I have to do this when I already know the area of a trapezoid? But here's the thing though, is that sometimes there's no obvious formula for a certain shape. Like it's considered example that I showed you at the very beginning. Such as this one. How are you going to find the area of that? Well, it turns out that if you had the coordinates of every point, like this, the really cool thing is that if you go in the right order, so like say you start here and you go like that, and you continue all the way repeating back to the beginning, then you can actually get the area of it without even knowing the lengths and the angles and all that complicated stuff. You just needed to know the coordinates and you're done. So that's what I wanted to show you in terms of like how to find the area of any polygon. All right, hopefully you found this really interesting. And if you are, then I seriously recommend that you check out my PDF. All right, everyone, have a nice day. Bye.